Okay, thanks very much for the opportunity to speak here and open this conference. So I will tell you primarily about a paper that finally appeared last night, but one of the key technical tools was already in this secret weapon paper, which has been online for over a year. And this is work done in collaboration with my great students, Diego, who's in the audience, as well as Kentaro Omori, who is unfortunately not in the audience. Okay, so let's start with some motivation and setup. What are we talking about here? So everybody here in this audience loves gapped phases in 2+1 dimensions. These are described by anyons, and we model them mathematically by topological field theory, at least for the class of phases that I'm talking about. That will be the model. So the world lines of anyons are topological, and as long as the system remains gapped, the topological field theory is robust. In particular, we're talking about systems with no local operators, so there's no local perturbations. The infrared physics has some stability. And it will be useful for us to introduce some language for this. At first, this will just seem like language. So the anyon world lines are codimension 2 topological operators, defects. So they're, in modern language, some kind of one-form symmetry. And the abelian anyons are what we would normally talk about as the abelian one-form symmetry. That's common even outside of topological phases. And then more interesting for us will be the non-abelian anyons, which are something like a non-invertible one-form symmetry. So this talk will be mostly about transitions between topological phases in 2+1D. And so when the gap closes, a transition can occur. And there are kind of broadly speaking two classes of transitions, and they're not really always distinct, but I'll just highlight them here. So there's fractional Hall transitions, which you could get by varying the external magnetic field in your problem. And there's a zillion papers on this, but I'd like to highlight this paper in particular, which has a lot of technical overlap and crosstalk with our work. So we'll come back to that at the end. And then for me, what I'll be focusing on are Higgsing transitions. So we'll be in a quantum field theory where we have a Higgs field, and this Higgs field can develop an expectation value, and that will change which topological field theory we're talking about. And of course, these transitions themselves could be gapped or gapless, depending on which model you're talking about. They could be first order, meaning you just have two TQFTs that coexist at the same point in parameter space. Or maybe more interestingly and more fun, they could be second order, which means a gapless, so typically CFT, strongly coupled CFT, with relevant deformations to two distinct topological phases. Okay, so now let's get more specific. We are talking about transitions driven by the Higgs mechanism. So our setting will be continuum field theory for a while at least, and we'll be talking about Chern-Simons matter theories. So these are gauge theories, and here's the notation I will use to talk about their short distance microscopic definition. So there is a gauge group G, and you should think that G is one of your favorite gauge groups, connected compact Lie group, e.g. SUK. Okay. There's a quantized Chern-Simons level, so K will be some integer, and we'll denote the group and the level by this subscript notation. There will be matter fields, in particular a scalar field that drives this transition. I'll always call this scalar field phi. It's in some representation R of G. You can consider all sorts of models with many scalars. I will primarily be talking about models where the representation is irreducible just for simplicity, not for any important restriction. And then, so with this gauge group and matter content, we will have some scalar potential. The potential has many higher order terms whose parameters are not important, but there's one that is very important, which is the quadratic term. And it's by varying that of course, we flesh out this transition. Okay, so here's a cartoon of the transitions that we're interested in. So we're going to vary the sign of m squared in the potential, and this will drive a transition where phi condenses. So here's where the quadratic term is very positive. You have a potential roughly like this, and some minimum at the origin. And at long distances, we get the topological field theory that we started with, the G level K. And if you change the sign of m squared, then you put the minimum away from the origin. And so now you Higgs the gauge group. So the Higgs gauge group, G, will be broken down to K with some new, to H, excuse me, with some new level, K tilde. So this H is whatever stabilizes the vacuum expectation value in your problem. And so more precisely, I don't really want to focus too much on the microscopic Chern-Simons theory, but rather on the fixed point, whatever it flows to, that sits in between these two topological phases. So one is this G level K theory, and we can think that this plus phi squared term that we add to the potential is a relevant operator coming out of this fixed point. And the other side is the minus phi squared term that we could add to the potential, and then we flow to this distinct TQFT. So we're really interested in this fixed point here. Okay, so what are our main questions here? This is all well-trodden territory. So the first question is, can we get some handle on this Higgsing transition using the ingredients that are visible at low energies? So at low energies, we saw that there's this GK TQFT, this HK tilde TQFT. So we know that there are these two TQFTs that are connected. And we'd like to understand, can we develop some sort of working model of what that transition point looks like? It's not obvious that that should be possible. You expect that since you ran a renormalization group flow to get to those two phases, that you lost degrees of freedom. So we're going to have to add something back to make it work. But we'd like it to be something that we can see using just that infrared viewpoint. So that's the first question. The second question is about the symmetries of the transitions. So these two TQFTs have lots of topological lines. They have invertible, abelian one-form symmetry, and they often have non-invertible, non-abelian one-form symmetries. And we'd like to know, can non-invertible one-form symmetries persist at the transitions? Are they always just some accident of the infrared TQFT, or can they sit in the middle as well? Now, of course, many examples have invertible one-form symmetry. So our focus here is on the non-invertible one-form symmetry. So those are the main questions. What will be the main results? So the first is I'll talk to you about kind of a mesoscopic, if you like, model of Higgsing based on these infrared ingredients, the two topological phases, as well as the degrees of freedom that we're going to have to add back will be some 1 plus 1D coset CFTs. And this is similar to a perspective introduced by Sopenko. You should compare this construction, those of you who are familiar, to coupled wire models of fractional Hall transitions. So that's the first thing I'll talk about, is how this model works. And this model, we'll see, is very well suited to address the second question about non-invertible one-form symmetries. And we will give you some examples where if you use this model, you would think that the fixed point has non-invertible one-form symmetry. So the transition has more than just abelian anyons that remain topological. Let me be a little bit more specific about the class of examples that I am interested in. So here's an easy way to build models with non-invertible one-form symmetry, which you might think diminishes the question that I am asking. So let's consider a theory with an ordinary zero-form symmetry group K, which is a finite group. And let's assume that K is non-anomalous and gauge it. So we're going to sum over some domain wall insertions for that K. And then the Wilson lines, for instance, form a representation of K fusion ring. And, okay, if K is non-abelian, that's non-invertible. Okay. So that's one way to generate examples of non-invertible one-form symmetry. And many models, interesting models of that have been discussed. Different aspects have been discussed. But that's not the focus that I have today. So those kind of examples do not teach you that much about renormalization group flows, because the operation of gauging a finite symmetry group is a topological manipulation. It commutes with the renormalization group flow. And so if your goal is to learn something about fixed points or some new dynamics, that's not going to help you that much. So I'm going to focus on examples outside of this class. So for instance, I'm going to restrict myself to connected gauge groups. That's one way to say what's different about the examples that I'm studying. Now, what will we get out of it? So what will be the punchlines? I'm going to go through a long song and dance about a model, some examples, but before doing that, I think it's worthwhile to highlight what interesting things you could learn from non-invertible one-form symmetry. Now, some of these things are not particular to whether the symmetry is invertible or non-invertible, but some things are particular, and I'll try to highlight those. So the first is, since it's a one-form symmetry, it can't be broken by local operator deformations. Therefore, it must be present in all phases that you get from the fixed point by relevant deformation. That's a well-known thing about one-form symmetry. Mathematically, what are we talking about here? We're talking about some kind of braided fusion category that's embedded inside this gapless phase. That's what it would be if the transition was second order. And then you can distinguish two sub-possibilities here. Possibility one is that this braided fusion category is modular on its own. It forms a little TQFT that lives inside your ambient theory. And in that case, the symmetry should decouple. That's a theorem if the whole thing was a TQFT, but it's natural to assume outside of that context as well. So that's maybe a slightly boring situation, though still interesting. More interesting is when the symmetry is not modular. So it does not form a consistent topological phase on its own. In this case, it provably cannot decouple. And then, in that situation, you expect new charged conformal defects. So you're learning about the existence of new objects at the transition point. So that's one thing you learn. Another thing you learn is about anomalies. So it's a well-known fact that the braiding of topological defect lines is an anomaly. What that means is that it has to be reproduced in all phases of the theory. Anything that you get by, for instance, relevant deformation out of the fixed point. And if the symmetry looks like rep K for some finite group K, if that's the fusion algebra, then the braiding could either be trivial or non-trivial. So that's always the situation we're in for standard abelian one-form symmetries. We have to do some further calculation, given the fusion rule, to figure out what the braiding is. However, if the symmetry is not rep K for some finite group K, and we'll have examples like that, then it's a theorem that the braiding must be non-trivial. So in this case, you get some anomaly for a non-invertible one-form symmetry that you detect just based on the fusion rules. So that's a little bit of a novel feature. And finally, the last thing I would like to highlight is that the energy eigenstates are going to be in representations of the symmetry, of course. And when this is non-invertible, it will be some kind of algebra, not a group. So it will be interesting to explore that more. Okay, so it's time to shut up about motivation. Let me start trying to show you some details of this model. And for more details, you can see the paper. So let's start with a kind of non-relativistic approximation. So we look in the case where the mass squared is positive. In the infrared, the theory is in this topological phase, this Chern-Simons theory, G level K. And these phi quanta are anyons. So I'll denote these anyons by A. So phi, the quanta of phi, gets described by some particular Wilson line A. And when the mass, so that's when the mass is infinite, so strict IR.
I'd like to ask the question. You say A is in GK, why do we mean A in rep GK?
Please.
So I'm confused about the notation. You say A labels the Wilson line, so should that be labeled by rep?
I'm abusing the in. I just mean that A is a representation in G.
Oh, thank you.
Yeah. Phi carried this representation. I just want to distinguish the scalar field in the microscopics from the anion in the resulting Chern-Simons theory. Just keep them conceptually distinct. Okay, so that's what's going on when the mass is infinite. What about when the mass is large but finite? Remember, our goal here is to be kind of effective field theorists looking up from the infrared. Well, then we should try to modify the vacuum to include virtual phi loops, or from the viewpoint of the TQFT, virtual loops of these anions, A. So here's some messy vacuum that we all see draw cartoons of in QFT class. Now there are problems sharpening that idea, actually. One is that this anion has non-trivial spin. So how are you supposed to do the sum? Another problem is that when anions collide, when these A-type anions collide, they produce some other kinds of anions. And you should include those in the sum as well. So you need some consistent rule for doing that. And third, we have this kind of intuition that we're missing degrees of freedom. And the question is, how can we liberate them? So we'll see that all of these questions kind of get solved in one swoop in a minute. Okay, so let's start by subjecting the theory to a position and time-dependent mass. So we're going to consider a domain wall here. So we're going to, instead of having m be a constant, we'll take m squared to be some function of position and time. And this will separate space-time into regions. Okay? So the first region is where m squared is positive, and then if we go to the infrared, it's that massive TQFT phase, G level K. And the second is where m squared is negative, and then if we go to the infrared, we're in this Higgs phase, H level K tilde. And then there are, of course, some codimension 1 regions, these domain walls, which are interfaces, and these will support gapless modes from the fact that the mass vanishes. What are these gapless modes? Well, we know what they are on general grounds. These are a 1 plus 1D coset conformal field theory. So I will write it this way, GK mod HK tilde. What that means, if you're not familiar with it, is you take the GK WZW model and you gauge HK tilde. And typically these modes are chiral, since GK and HK tilde do not have the same central charge. So there's some chiral modes on this wall. Okay, so now let's try to make a model.
Coset conformal field theory is not chiral. If you just do...
I'm doing a chiral half of it.
So that's not what you said you're doing. It's not taking the WZW model and...
Sorry, you're right, yes. I mean a chiral, you're right. I mean the chiral half of this. Yeah. Thank you. Okay, so now, so that was about domain walls. And now I'd like to make space-time into a network of these domain walls. And I'm going to try to do this to build up a model of the transition, right? My goal is to describe this Higgsing transition using kind of infrared degrees of freedom. And here's how I'll do it. So I'm going to arrange m squared to be negative inside a regular cylindrical grid in space-time. So here's this grid. So there are these tubes. The purple region is the domain wall. Okay. So here's a cross section. If you cut at some constant time slice, you get this. So outside these tubes, the mass squared is positive. You're in the GK phase. That's here. Inside, you're deep in the Higgs regime. The mass squared is negative. That's the HK tilde. And on the tubes, that is on these little regions here, that's where you find this chiral coset modes. Okay. This is kind of like a lattice model, except for I'm not giving any microscopic definition of the Chern-Simons theory. I'm assuming that you gave me that. So that's why I call it a mesoscopic model. So there's a kind of lattice spacing, if you like, which is the distance L between nearby sites. And then there's a width here of the cylinder W. And these cylinders are gapless. So this is our kind of Euclidean lattice model in quotes. And now as we vary the parameter W, the width of the cylinders, at fixed lattice spacing, this model will realize distinct phases. Okay? So if I increase W, keeping the lattice spacing the same, I kind of blow up this mesh like that. And in extreme limits, I get, therefore, both topological phases that I wanted. So if I collapse the network, that's one limit, W to 0, then I get back to this GK topological phase. And conversely, if I expand it such that the nearby cylinders merge like this, then I get this HK tilde topological phase. So this model presumably realizes several different phases, these two in particular, and our kind of basic hypothesis is that somewhere in the parameter space of this model is the Chern-Simons matter fixed point that we were talking about at long distances. That's our kind of working viewpoint. Okay, I kept saying the words missing degrees of freedom. I'd like to try to sharpen that a little bit. So I'd like to tell you about why this model, you should think of being able to reproduce the quantum field phi. So in the Chern-Simons theory, one interesting point is that the anyons A, which are these IR phi quanta, cannot end. Right? There's some topological lines that don't break. By contrast, in the fixed point theory, A should be able to end on this field operator phi of x. Okay? And this behavior is reproduced in the mesoscopic model. So the basic point about this chiral coset mode is that they have local operators, O, these are vertex operators, and these operators can absorb the anion A. So here's the picture. So the anion A can come from outside in the GK phase. It can hit some vertex operator on the coset, and then it doesn't continue inside. That's actually the distinguishing feature of the coset. So equivalently, when A transitions through the domain wall, it becomes transparent. And this is already a hint of something that's to come, which is that, that A inside the wall has condensed. So we'll talk about that soon.
I would expect, I would expect that, like, when you take an anion from the GK theory and you try to put it through the coset, it will decompose according to the branching rules, no? So something would come.
Yeah, that's great. That's exactly right. But the coset, the H is exactly the group that, we'll do that kind of more generally soon, but H is exactly the group that has, where R has a channel to the identity. So that's why this, this diagram is right. Okay, so that was a kind of a Euclidean model. Let me briefly flash that you can also develop a Hamiltonian picture by just trying to quantize that time slice. I won't give you too many details, but the Hilbert space would now be a tensor product over the coset states at each site. And we should also include some states from the GK TQFT describing the description of these thin tubes that you would get by contracting down the cylinders. And then the Hamiltonian will have two parts. The first is the free part, if you like, free in quotes. That's decoupled coset energies at each site. And then the interaction terms are terms like this. They're anion exchanges between nearby sites. And you could ask, what's not included in this? Well, what's not included is I'm not allowing you to put anions in the middle of the HK tilde cylinders. So that's like, that's my kind of effective field theory hypothesis, that I don't need them to describe the transition. Okay, that's the model. Let me tell you a little bit about its symmetries. I'll have to speed up a little bit. So, okay, as for the question in the back, so our model is well suited to investigate one-form symmetries. So, in general, if you have a line chi in GK, it can transition via coset vertex operator to some other line psi in HK tilde, and that's given by the branching rules. That's something that you can work out. And most vertex operators carry energy or spin, and therefore are not topological. So most of the time, that O there is not topological. So even though chi would be topological in GK and psi would be topological in HK tilde, this composite operator is not topological. So this is these transitions typically break one-form symmetries. Now an exception, and what we're going to focus on, is that if a line can transition via topological local operator, then it will define a one-form symmetry that's preserved over the entire phase diagram. So here's an example of such a junction. So this is our way that we're going to identify one-form symmetries. So you can get more precise and say that what we're doing here is we're going to track lines through the domain wall using anion condensation. That's the technical tool that's in play here. Okay, so the key thing that we need is the 2+1D coset TQFT that has as its one-sided edge this chiral coset CFT. So I denote that this way. And we have a presentation of the Higgs phase, HK tilde, as resulting from the product of the massive phase, the coset TQFT, and a condensation of some non-simple anion B. Okay. So this is an equality of 2+1D TQFTs. We'll study examples like this. And in particular, this object B that is condensing will contain a term like this, A rho bar. Remember, A is the infrared avatar of the phi quanta. So what we're having here is that in this model, the Higgs mechanism is the same as anion condensation. And that's what's giving us our technical power. Okay, so the coset degrees of freedom that I introduced, they solve the problems of the non-relativistic approximation that I talked about. So first of all, the elements of B that can condense have integer spin. So for instance, even though A didn't have integer spin, it pairs up with some coset mode to become a boson. The fusion rules of the algebra dictate the consistent sums of products. And this gives us a recipe for non-invertible one-form symmetry. We identified lines, a chi, in the massive phase in this way, and we put them inside the massive phase times the coset, and then we check, does chi remain topological as we go into the Higgs phase? That's a question of what happens to this line after we condense the algebra object B. That's something that we can do. Okay, so I have only a few minutes left. I'd like to quickly go through one class of examples that have non-invertible one-form symmetry. You can do simple examples, of course, that have invertible one-form symmetry, but let's get to an interesting one. So these will be unitary gauge theory examples. So we'll talk about the gauge group SUK level 2, and the matter will be phi in a symmetric tensor representation. So a single symmetric tensor scalar. And the Higgsing is that we can tune the potential so that phi develops a expectation value that's like delta ij. So this is our RG flow diagram. The massive phase, phi is just lifted, and you get SUK level 2. The Higgs phase, phi condenses, and it breaks SUK to SOK, and the level jumps. Okay, so what's the claim about this fixed point theory? This fixed point theory has PSU2 level minus K symmetry. That's the claim. So this, what I mean by that is it's the fusion subring of SU2 level minus K, which happens to be uncharged under the Z2 center. So that's in general some non-invertible one-form symmetry. And to work this out, it's useful to know that the relevant coset, SUK over SOK, has a level rank duality to a parafermion theory. Okay, so here's the simplest case where you find non-invertible symmetry in detail. That's SU3. And so the claim in this case is that the symmetries at the fixed point are some Fibonacci line. So somebody L such that L times L is 1 plus L. In this case, for K equals 3, the PF3 is the same as the 3 states Potts model. So here is SU3 level 2 with its lines. And here's the 3 states Potts model. And the nice thing about this example is that the condensing algebra is abelian. So here is the thing that you condense to investigate the transition to the Higgs phase. And so 6 is our matter scalar. So there you see the identification of Higgsing with anion condensation. And it pairs up with a friend Z in the 3 states Potts model to cancel its spin. And what you can check is that the preserved symmetry line L is the 8, the adjoint, which indeed has Fibonacci fusion rules, And this matches across the domain wall with the Fibonacci anion of an identical spin in SO3 level 4. Okay, let me give 1 minute of a consistency check via the duality web. By duality web, you might wonder, we've had some questions already, so I'm going to absorb a few minutes of questions. So, so you might wonder, how do I know this is true? Can I subject it to any consistency check? Here's one thing you can do. Take this whole proposed SUK level 2 diagram, this flow diagram, and tensor it everywhere with a decoupled TQFT, SU2 level K. Okay? Now, if this model that I was talking about has the symmetry that I said, then that means in all phases there will be a condensable center algebra inside this product. I'll call that dk. It's the sum of these representations. This part is because secretly this model has that symmetry, and this part is because I tensored it with something decoupled. Now I can condense this anion in all phases of the theory, the UV and the infrared phases. And I use two-level rank dualities here and here, so that this is the same as SU2K level 1, and this is the same as SP2K level 1. And what this implies is that from our flow, we get a new flow diagram, which is this one. And consistency check is that this is indeed a consistent RG flow diagram. So that's kind of a duality web style check. If you propose a new fancy symmetry, you could try to gauge it and see if you get something consistent. Here we have that. Okay, last technical slide is I want to tell you something about the modularity and the symmetry TQFT in this example. So it's interesting to try and realize this symmetry by a 3+1D TQFT. So the relevant theory in this case is rather easy. We just have a Z2 dynamical two-form field B, and the point is that the boundary of B, Wilson surfaces, are identified with the center of SU2 level minus K, and they're gauged. And the bulk action for this two-form is dictated by the spin. So we have the Pontryagin square here, and K is the same K as the SUK. And notice that this means that all the symmetry lines that I was talking about are confined to the boundary. They don't escape into the bulk of this symmetry TQFT. And we have a bifurcation of two cases. One is that K is odd. In that case, this symmetry is modular on its own. The bulk is invertible, and this symmetry should decouple. And the second is that K is even. Then the bulk is not invertible, and this symmetry is not modular, so it cannot decouple. Okay, that's my examples. We have more examples in the paper, but let me sum up. So we're trying to model here Higgsing transitions between topological phases mesoscopically using something like a coupled wire or a domain wall network model. And one of the things that I told you is that once you latch onto that model, you can find examples where there's non-invertible one-form symmetries present across the phase diagram. And these are interesting in that they imply new conformal defects, new anomalies, and perhaps some interesting representation theory to explore. Future directions. I think I've really unpacked all the dynamical consequences of the non-invertible symmetry here. There's more to do. And finally, let me come back to this very interesting paper, which modeled fractional Hall transitions by anion condensation. And it would be great to make a sort of sharp connection by thinking of their model from a varying magnetic field point of view and comparing. So that's work to do. Thank you very much.
Thanks a lot for the nice talk. I have a question about this condensation. If you can go back to the slide with the where you have B. So maybe this Fibonacci example is actually nice. So I think I asked you this when you gave this talk at the first week of the program. Is it true that the fusion category symmetry, topological defect lines that Shuheng et al. Worked out in CFTs, is that always so part of the defects that actually govern this particular transition? Like here, Fibonacci is part of this coset model, for example. Right, so the coset CFT has topological defect lines, and so in this case it's three-state Potts, which has a Fibonacci symmetry and a Z3. So is that the thing that actually always governs these transitions, or a subset of those lines?
Probably, but let me punt again. But let's talk afterwards. I think you're probably right, but yeah.
So you started by assuming that the transition is second order, but can you use?
Not really. No, I mean.
Not really? Oh, okay.
No, I mean the same discussion would apply if it were first order. Maybe it would just be more boring.
Okay, but can you use this mesoscopic model to predict or at least argue in some cases whether the transition is second order or first order?
I don't know how to do that yet.
Oh, okay, thanks.
Yeah, I just had a question about the dynamics of the transition. So in this anion condensation interpretation, you said that in the GK to HK tilde transition, you stacked with this additional thing, and then you condense this B. Is that the? So dynamically, if I took a theory that's the parent phase is already the step, the GK times GK mod HK tilde theory, and then you go to a HK tilde phase. That's a different Higgsing transition from the transition that goes directly from GK to HK tilde. Is that right?
I'm not sure I exactly understand the.
So algebraically, I think this condensation this equation makes sense to me.
Yeah.
But from a dynamics perspective, the transition you're describing is from GK to HK tilde.
Yeah, but so this is just a way to track the lines through the through this domain wall network picture.
Right.
So the point is that this domain wall network is engineering that anion condensation.
But are you saying that the critical point, if it's second order, is the universality class of the original transition the same as the universality class of this bigger TQFT to HK tilde transition?
I don't know if I'm saying that. I'm just saying that that this is the thing that has the edge modes that are on those domain walls, which is why it tracks what happens when a line comes from outside and pierces a vertex operator and then goes inside.
Right. Okay, so I should not think about this as the same dynamically as the transition in which you're condensing the B inside some larger TQFT.
We weren't thinking of it that way.
Okay, got it.
I got a little confused about one global issue. So on these tubes, you're putting some chiral algebra degrees of freedom.
Yeah.
And presumably because there's GK and HK twiddle on either side, the MTC associated with this chiral algebra should be GK times the orientation reversal of HK twiddle.
Yeah.
But the coset sometimes is an anion condensation thereof.
Yeah.
So am I always allowed to place this coset chiral algebra on these walls? Or?
Yes, and in fact, the anion condensation in the bulk TQFT is usually necessary to get the right edge mode coset.
Right. I just thought that you always have to put stuff on these tubes that has the correct MTC, and it just seems like they might differ by some global difference.
Do you have a comment you want to make, Diego?
That will just be given by the coupling of the lines inside and outside, like in the GK and HK tilde. So that may give you like the coset MTC times maybe some topological sector. That may happen.
I had a tiny technical point on your next slide. Sorry, there was one with a B in it. Maybe it was the previous one.
A B?
B, the condensing B in this product.
Okay.
I think you said, in this case, we're in a good situation that it's abelian, but I thought the B is always abelian.
No.
That's not happening. Okay.
No. In general, B is non-abelian. That's an interesting point. So yeah, so B can be abelian or non-abelian. The non-abelian case is more technically challenging, but we have examples like that too. Okay.
So in the gap phases, you have this ground state degeneracy, which in a finite size system has this exponentially small splitting with system size. At the critical points, some of those states could get split into some power law splitting with system size. And I think the presence of these kind of interesting, one-form symmetries will have implications for when you have exponentially small splitting, when you have power law splitting. I wonder if you've thought about that.
I haven't thought about it yet, but let's talk about it.
Okay. Can I ask one more question?
Yeah, go for it.
There's another class of transitions, which are Chern-Simons Dirac transitions. And those allow you to change the level.
Yes.
And whereas like the assumptions, I think like the main assumption of your theory, you would have treated it the same way.
I would have more or less treated it the same. I mean, here for me, I took HK tilde. The K tilde is what you get from K plus the index of embedding. It's the new level. I think I would have treated it much the same, but there are some finicky details about fermions that you'll have to get right, but I think you might imagine that there's something similar there.
Yeah, I have a question about the interfaces in your mesoscopic model. You have these circles that are compact, and there's boundary conditions on them. So is it just the zero modes, or more precisely, how do you count the zero modes that survive to get the infrared physics?
Sorry, zero modes of what? Sorry.
Well, if it was a free fermion, it depends whether there's a zero mode or not, depends on whether you have periodic or anti-periodic boundary conditions. The gaplessness just guarantees that it's locally gapless, but not globally on the circle. So I'm trying to understand.
So when I quantize on the circle, if I try to do in the Hamiltonian framework, I'm including all the states of not just the zero modes. I'm including the whole tower of coset modes.
Okay, but then it's not really local field theory at the, let's say, lattice scale.
Each of these has a lot of states. It's not a finite Hilbert space.
Okay.
So, as far as I understand, this one-form symmetry that you get is because the coset has universes. No, the fact that you do the anion condensation is to take away the universes in the coset. If you have the full coset, right? That's usually what happens. If you take the naive coset, you have many vapua, and then you have to condensate.
Yes.
But okay, then this chiral domain works because you don't know the chiral situation very well. Do they have a single vacuum, or are they also degenerate?
It depends on the model.
Okay.
One more question. Thanks for the talk. I have a question. So I'm having trouble understanding this picture when W is larger than L. The width is larger than the distance between.
Yeah, maybe I should try. I mean, we're not great artists here, but I can try to show you. Maybe I could try to sketch it afterwards. But okay. Yeah, it's the network merges, and the kind of boundary of it kind of goes off to infinity as W goes through L. So I'm sort of letting the cylinder, when they come near to each other, I'm saying that they open up and become, they merge. We tried to draw that, but let's see. Where did we try to draw it? Here. You see, like I let them merge. And then when these come here, they're going to merge also. And so like there will be fewer and fewer cylinders. The interior will fill everything.
So for each value of W and L, you have a specific mass-dependent mass profile.
So yes, I mean, you could say I can write down a function, if you like that would do that. Uh-huh. Yeah.
And one other question, in the specific examples, can you verify that, once you do this picture, you get this coset, or is it just an assumption that you get the coset and the interface? Or can you do it in the specific example?
You mean if I take an actual scale model with the scalar varying mass, do I get the coset, or do I differ by some maybe topological sector? Is that the question?
Yeah. Is that if you change this large W, is that exactly what you get?
Definitely in the examples that we talked about, and I think perhaps up to a topological sector. I'm confident of it, but let's talk about the topological sector.
Okay. Oh, that's great. Thanks.
It's a question of sort of how many junctions, but not the existence of junctions.
Sorry. As far as I understand, for the sake of your argument, it would be enough to have one defect, right? Separating two phases. And then when the mass is big, then it's clear that you have a degrees of freedom fixed at the interface, but when you go up towards the ultraviolet, this kind of this interface tend to disappear, and then you match the degrees of freedom. Is that correct?
If your goal was to just match the symmetries across the transition and make it plausible, you would probably content yourself with saying, here's one defect, here's one domain wall, and let me see how a line penetrates through, and do the same coset type calculation. I was trying to give a more, the first part I was trying to give a more dynamical perspective about why that would really be enough. But indeed, it's quite plausible if you just content yourself to looking at one domain wall.
I have one question there. Can you use mic?
Yeah, I was wondering about the transition point. You said it's like it could be a gapless transition. Is it clear how the conformal symmetry emerges there, if at all?
No, I mean, this is something, I mean, it's not exactly a lattice field theory, but, you know, it's something close to that. So I think your question is a bit like, how would you see conformal symmetry in a lattice model, which in general is very hard.
Nice talk. I have a comment and a question. So the comments are related to Sakura's question as well. So in this theory, in this gapless theory, you can consider boundary conditional theory by doing a half, RG on half space, particular of the type that you considered. So if you consider a boundary condition that corresponds to two gapped faces for this fixed point theory, and you fuse them, I suspect you will get this chiral theory. And then that's related to Sakura's question, because then the topological lines in the box CFT then will become naturally topological lines in the two-dimensional theory. So that's the first comment. The question is, from this exploration, do you see any general constraints on the operators at endpoints of topological lines, especially in an invertible setting? In the 2+1.
No, I mean, I think that goes under the kind of future work. I mean, that's sort of here. That's one of the things I would like to explore. Is
have you studied in any of the examples?
Not really yet. I mean, almost everything we know is in the paper, and most of it was presented today. Yeah.
I'm gonna look at the paper. Thanks.
We have one last question.
In general, I think you have a choice. I mean, I agree that if you literally take the mass and vary it in the way you described, you'll probably get this coset of affine Kac-Moody algebras. But in general, you actually, there are many choices of chiral algebras that you could have placed on these twos.
Yes.
And they would ostensibly describe a transition between these same two gapped phases. So do you have any priors about whether the fixed point will remain the same? Or?
I don't know. I mean, one of the points of view that we were taking is that, you know, as compared to people who might do a kind of a general coupled wire model, where you might say the Hilbert space on each side is your option. If you say, I want to hit the Chern-Simons fixed point, you have actually the microscopic Chern-Simons theory to start with. So we try to put the edge mode there that is what is dictated by the Chern-Simons theory. So that was our viewpoint. But you're right that you could just say, let me take a more broad point of view, forget the UV microscopic Chern-Simons theory and what it predicts. Just say, I have two separate TQFTs, and I figure out some gapless interface between them on these little tubes, and that is some kind of model of the transition between them. So you're right, there's kind of an open landscape of things to explore there.
Okay, we can thank the speaker.